Welcome to Binary and Decimal Math. In the last video with Binary Math Basics, we talked about how binary is the language of computers and it represents a value state of on or off. So every binary place has two possible values. Now, in our world in IT, we work primarily in two different versions of this. Either in an 8-bit set known as a byte or a 4-bit set known as a nibble. So, what we want to do is we want to look at these values. And the core to remember is that as you count up in binary, you count right to left. This is opposite of what you're used to, but this is how, and it doubles every value right to left. So what you're going to do, you're going to start with your first value, and your first value will be 1. Your second, 2. Double that to 4, double that to 8, double that to 16, double that to 32, to 64, to 128 in an 8-bit set, also known as a byte. Now, if we add up all of these values, we get a total of 255. Now, if you recall from the prior video, I said there are 256 total combinations of values in an 8-bit set. That's because 0 is a value. So if all of these bits were turned off, that gives you a value of 0, or your 256th value. A 4-bit set works just like it, just half as big. 1, 2, 4, 8. Fairly straightforward. So let's look at binary to decimal math. So in Ipv4 subnetting, and Ipv4 addresses, we work in what we call decimal math. This is a number with a value of 0 to 255, which is representing an 8-bit binary combination. We use this in IPv4 to identify the address of a machine. So let's start with looking at this one. In an 8-bit set, and this is referred to as an octet, and I just realized you can't see the last numbers there with this displayed this way. How about that? In an 8-bit set, you're going to be able to see this as it's an octet, right? 8 bits, octopus, octagon, 8, octet. The binary value, though, indicates which bits are on or off. So in the following example, let's count this up. So the 128-bit is on. So we're going to say 128. The 64-bit and the 32 bits are off. So these have 0 value. The 16-bit is on. So we're going to say 128 plus 16 plus 8 because the bit is on plus 4 because the bit is on. We're going to skip 2 because its bit is off plus 1. So 128 plus 16 is 144. Plus 8 is 152. Plus 4 is 156. Plus 1 is 157. In the next slide, we see that's correct. And it explains it right here. If the bit is on, then we're going to apply that value of that bit to the total. We are only going to add the bits that are on. So let's try a few more. I'd like you to work your way through these, pause the video, and then see if your answers match what we have in the next slide. So if you did pause the video and you didn't just look up to the corner to get your answers, you'll see that the first one should be 69. Because 64 plus 4 is 68, plus 1 is 69. For the next one, we can look at it and see that all the bits are on except for the 1 bit. And we established earlier in this video that if all the bits are on, we get a total value of 255. So if we're only taking 1 away from it, then this one's going to be 254. In this one, we can see 128 plus 32, that's 160. Plus 8, 168, plus 2 gives us a total 170. In this one, the fourth one, all these are off. So we only start adding once we get to 4. 4 plus 2 plus 1, 7. And so on and so forth. You should have gotten 227 for this one, 204 for the next to the last one, and 185 for the last one. And you can validate your math that way. Binary math is not terribly difficult. It is a concept of just understanding that each of those bits has a value. So with that, you can take and do the math, do the addition, to get what your decimal value is, or your decimal representation of an 8-bit or 1 byte or octet value. All right. So now let's reverse the process, because we can do the exact same thing. We can do what is called binary subtraction. So with that, what we're going to do is we're going to start with the same binary grid from 1 to 128, right to left. But for the sake of doing the subtraction, we're going to do the math from the left to the right. So we're going to look at our number, our decimal value, determine if we can subtract our decimal total from the bit position, and have a number greater than or equal to 0 remaining. If you can subtract, then you're going to subtract the bit position from the decimal, and you're going to give that bit a value of 1. And then you take your remainder and move to the next bit location and repeat the process. Once your remainder is 0, then all other bit locations from the left to the right will also be 0. So let's look at one. 212. So we can say 212. Can we subtract 128 from 212 and have a value of 0 or more remaining? And the answer is absolutely, we can. So we do that subtraction, and we have a remainder of 84. I think that's right. Yes, we have a remainder of 84. Sorry. And you can use a calculator to do this part. That's not a big deal. So the 128 bit is on. So from 84, can we subtract 64? And the answer is yes, absolutely, we can. And then so that bit turns on, and we have a remainder left of 20. Can we subtract 32 from 20 and have a number greater than or equal to 0? And the answer is no, we can't. So we're going to leave 32 off. Can we subtract 16 from 20 and have a remainder greater than or equal to 0? And the answer is yes, we can. So we'll turn 16 on, and we have a remainder of 4. Can we subtract 8 from 4? No, we can't. So it's a 0. 4 from 4? Yes, we can. So we're going to turn that one on. With that, our remainder is 0, which means the last 2 bits have to be 0. So we're going to set those to 0. So what it'll look like, the binary representation of 212 is 1101010. And there's wording here on exactly how that was done. If you didn't follow that, let's read through that again. 212. Can we subtract 128 from 212 and have a positive or 0 remaining? Yes, and we have a remainder of 84. Can we subtract 64 from 84? Yes, we have a remainder of 20. Can we subtract 32 from 20? No, we can't. So this bit gets turned off. Can we subtract 16 from 20? Yes, we can. So this bit gets turned on, and we have a remainder of 4. Can we subtract 8 from 4? No, we can't. Can we subtract 4 from 4? Yes, we can. So that turns on. At that point, our remainder is 0. So the remainder of the bits are also 0. All right, let's do some more. So work through these on your own. Pause the video. See if you get the right answers. And let's go through them then after you get done with that. Assuming you paused the video, then let's dive right through them. 255. 255 is the cumulative total of all these numbers. So if you say 255 minus 128, minus 64, minus 32, minus 16, minus 8, minus 4, minus 2, minus 1, every one of these bits will get turned on. So these will all be ones. 177. Can we subtract 128 from 177? The answer is absolutely we can. So that gets turned on. And 128 minus 77 gives us a remainder of 49. So 49. Can we subtract 64 from 49? No, we can't. Can we subtract? So that gets turned off. 32 from 49. Yes, we can. That turns on. We have a remainder of 17. 16 from 17. Yes, we can. Turn it on. We have a remainder of 1. 8 from 1. No. 4 from 1. No. 2 from 1. No. 1 from 1. Yes. So we're going to turn that one on. 83. Can we subtract 128 from 83? No, we can't. So that's a 0. Can we subtract 64 from 83? Yes, we can. So that's a 1. We have a remainder of 19. 32 from 19. No. So that's a 0. 16 from 19. Yes. So that's a 1. And we have 3 left over, right? So 8 from 3. No. 4 from 3. No. 2 from 3. Yes. So it would turn on. We'd have a remainder of 1. 1 from 1. Yes. So this would turn on. And follow that same process for the remainder. You should have gotten answers like this. So the binary representation of 49 should be 00110001. And that's really all there is to it. Now, Ipv4 addresses are 32-bit addresses, but we represent them in 4 8-bit octets, all right, 4 bytes. They're given in decimal form, and your computer and its logic will change this to binary. With an Ipv4 address, you're given 4 decimal numbers separated by a decimal point. All right. So an example of an Ipv4 address is 192.168.1.23. Let's break it down in binary. 192. Can we subtract 128 from 192? Yes, we can. We turn it on. We have 64 remaining. Can we subtract 64 from 192? Yes, we can. We turn it on, but we have from 120. Sorry, back that up. With 64 remaining, can we subtract 64 from 64? Yes, we can. We're going to turn it on. But now we have a remainder of 0, so all the rest of those bits are 0. 168. Can we subtract 128 from 168? Yes, we can. Turn it on. We have a remainder of 40. Can we subtract 60 from 40? No, we can't. That one gets turned off. 32 from 40? Yes, we can. Turn it on. We have a remainder now of 8. 16 from 8? No, we can't. 8 from 8? Yes, we can. Turn it on. Our remainder is now 0. Turn everything else off. 1. 1's an easy one. We can just look down here and say, okay, well, value of 1, it's all zeros, 1. 23. Can we subtract 128 from 23? No. 64 from 23? No. 32 from 23? No. 16 from 23? Yes. Turn it on. We have 7 left. 8 from 7? No. Turn it off. 4 from 7? Yes. Turn it on. Remainder of 3. 2 from 3? Yes. Turn it on. Remainder of 1. 1 from 1? Yes. Turn it on. Remainder of 0. So this string, we put these all in a row, is our binary representation of that 32-bit address. 11000000 10101000 00000001 00010111. That binary string is your representation of this IP address. So what I'd like you to do next, convert these to binary. And what you're going to do is work through and just do each individual section and get your string output, and let's see what you get. Pause the video and work through those now. Assuming you paused the video and worked through them, these should be your answers. For the first one, you should, for 237, you should get 11101101. 56 should be 00111000. 105 should be 01101001. 68 should be 01000100. And so forth for the next. Go ahead and pause the video, validate your answers. But essentially, that's all there is to it. Now, if you want to go from binary to decimal, so if you get one of those 32-bit strings, you're just going to do the exact same thing in reverse. So what you would do, say you had this big 32-bit string right here, right? Just take, and even if they weren't separated with the decimal points, just take and put a line in for every 8 of them. Then take that 8, plug it into your 8-bit values, and do the addition. So like we could look at this last one and say, okay, 1 plus 4, so now I'm at 5, plus 8, so now I'm at 13. The 16 values off, the 32 values on, right? So 13 plus 32, now we're at 45, and the 64 values on. So now we're at 109. All right? All right. That's all there is to it. And you just work your way backwards across it. And that's it for this video. That's all there is to binary decimal math. It is as simple as laying out your 8 bits, assigning the proper values of them being on or off, and doing the addition or the subtraction as necessary to go from decimal to binary or binary to decimal. We'll cover this a little bit more during the class session on Tuesday. But overall, a lot of what we'll do on Tuesday will be practice. If you have any questions, reach out to me. Otherwise, go ahead and work your way through these and be prepared that we're going to go on in the next video when we're going to talk about hexadecimal using 4-bit combinations.